So I will now continue with the session. So this session would be chaired by Professor Amitabh Lahiri of SNB NCBS. So I would like to invite Professor Lahiri onto the podium. I would also like to present Professor Lahiri with a small memento.
Good afternoon and welcome back to the post-tea session. Today's sessions are of course a bit delayed because of the inaugural program. So this is the post-tea pre-lunch session. And the first talk is by Professor Subir Sachdev of Harvard University. So I invite Professor Sachdev onto the stage. So we are probably starting a bit early, but anyway. So he'll be speaking on from the Sachdev E-Kitaev model to theories of strange metals and charged and rotating black holes. Subir.
Well, thank you very much, Professor Lahiri, and the organizers for inviting me to this great conference. It's a real pleasure to be here. All right, so I expect it's a fairly diverse audience, and I don't think there's anybody here who's really an expert on black holes, but don't worry, I will just very briefly comment on the application of black holes. So my interest in these topics was very much motivated by the experiments on the high temperature superconductors already in the late 80s, early 90s, showing very mysterious behaviors. And I'll comment upon those properties later today. We still have some ways to go to fully understand these mysterious behaviors. But that led me with my first student, Jinmu Ye, to propose a simple model which we thought could at least start the process of understanding this mysterious physics of the cuprates, and I'll say a little bit about that a bit later. But to my good fortune, the model has had its most direct application to an entirely different field of physics. So I'll begin by just describing the model, or its current version of it, which was proposed by Kitaev, which has the same properties but is a lot simpler to analyze further. Anyway, so let me describe the model as a model on its own right. It looks like a toy model, which may not have anything to do with anything, but I hope to convince you by the end of the talk that it actually is very useful for many things. All right, so here's one way to think of the model. Imagine you have a bunch of sites, which I've labeled from 1 through 19, and these could be actual positions in some material, or they could be labels of some orbital. It's just some quantum numbers. And then we occupy some fermions on these quantum states, some fraction of them. I ignore the spin of the fermions. And now I allow these fermions to move, okay? And the one constraint I will put is that there's no term in the Hamiltonian that allows any fermion to move on its own. So basically, but I will allow all other processes. So for example, there could be this process, which I'll call U11, 12, 5, 14, where a fermion goes from site 11 and 12 to get to 5, 5, and 14. So this process is associated with a complex number. This is a complex number giving you the quantum amplitude for this process. And so similarly, you can now pick of order n to the, there's n states, there's order n to the 4th processes, and each one of which will be associated with a complex number. What is that noise? Sorry. Anyway, so basically I can assign for any such two-body process a complex number. Now, of course, I have to solve the Schrodinger equation for the time evolution of the state of the electrons. All of these processes happen at the same time. They happen in parallel, and I have to integrate differential equation. But it's essentially impossible to do it for a large system because the total number of states is of order 2 to the n, where n is the number of sites. So that grows very rapidly, and once n becomes bigger than 30 or 40, it's impossible to really predict with any confidence what the system will do. All right, so what we realized that you can make some progress with one very simple assumption, and the assumption is that these numbers this list of numbers that you gave me are uncorrelated random numbers. That is, they are independent random numbers. That's really the most important assumption. And it turns out with that one assumption, you can now predict lots of things in the large N limit, which is what we did already in 92. And today we know much, much more, thanks to a lot of brilliant work by string theorists who, as I'll explain, also got interested in this model more recently. Okay, so that's the model, and here it is written out in formalism. You have some second quantized formalism. You have fermions hopping between these n sites, and there's an amplitude u alpha beta gamma delta, which we could take to have zero mean, and some mean square value u squared. And the most important property is that the different u alpha beta gamma delta are uncorrelated random numbers. So how does the large N solution proceed? Well, you can understand it quite simply, even in terms of perturbation theory. So if I just do perturbation theory in the U, so here's one graph that appears at order u squared, and here's another one graph that appears at order u squared. Then I put in all the indices, and then I average graph by graph. So what happens is, for example, this graph, there are 3 free indices, beta, gamma, delta, and there's a factor of n cubed, which comes from this factor of n to the 3/2 that was judiciously placed over there. So the sum over beta, gamma, delta exactly cancels the n cubed, and I get a term of order 1. Whereas here, there's a fewer independent indices, and you just get something that's down by 1 over n. And now you can go to higher orders, and you can go to all orders, and you would then find that as n goes to infinity, there's essentially only one graph that survives, which is this graph. Sometimes now people call it the melon graph. And also melons within melons. So you could put in this Green's function here has to be the full self-energy. All right, so, and so on and so forth. So melons within melons, there's an infinite set of graphs, but they all have this simple picture or its iterations. And all of those graphs can be summarized in these 2 very simple equations. This is just the Dyson equation for the average on-site Green's function. And this is the self-energy, which is just given by this one graph. That's this graph right here. It's only a function of time because all sites are equivalent to each other. So there's no space as such. And that's it. So these are the 2 equations you have to solve, and this fixes the total density of electrons. All right, so these were equations I wrote down in 92, and I thought, well, we'll solve these somebody must have solved these equations. No one's had ever actually solved these equations. And we said, okay, we'll figure it out in a few weeks. Well, we're still learning new things about these equations. Including, now a lot is understood, including the subleading singularities. But understanding those subleading singularities required input from quantum gravity, amazing as it is. But that's true. So let me just give you a flavor of exactly how all of that works. So when you solve these equations, you find its distinguishing features is that you don't have any quasi-particle excitations, no bosons, unfortunately, or fermions, or anyons, or anything like that, but just some entangled quantum soup. And so how do we know that? So just by looking at these equations and solving them, this was already done, especially in some important work by Georges and Parcolet a few years later, you find that the Green's function satisfies the scaling form, and this function f1 is known. And here's some pictures of what those functions look like as a function of different electron density. But the most important property of this function is that the natural line width of these functions at low temperatures is just temperature. So that's what's called Planckian dynamics. And from the point of view of Boltzmann theory or conventional perturbation theory or Fermi liquid theory, that's extremely surprising because all line widths in the end depend on the strength of the interactions. But here, they don't. The line widths, which you can characterize by some time tau of omega, which you can define from G, is just of order 1 over temperature. Okay, so that's one basic property. The other basic property, which came in this later paper in 2001, was a bit of a surprise and also a bit discouraging at that time. And what we found was that this model had a non-vanished extensive zero temperature entropy. So this means that if you compute the entropy and then take the limit as defined here, you would get non-zero value. Now, any model that had been studied in any generic model of many-body physics, this number S0 is 0. So this seems to be violating some third law of thermodynamics, but, well, depending on your perspective, it is or it isn't. It's really, but the order of limits has to be taken very carefully. It's really not a ground state degeneracy. It's zero temperature entropy. So there was one model and its cousins, the so-called Pauling's ice model, that has a zero temperature entropy because of some huge degeneracy in the ground state. So in that case, it's due to a ground state degeneracy, and the order of limits doesn't matter. But it's a highly finely tuned model. Only for very specific couplings does that happen. Here there's no fine tuning apart from removing the single body hopping, but otherwise the parameters are arbitrary, and you get this. And the way it happens is, if you just look at the density of states, these are all the many body states from some numerical study, is that the density of states is exponentially small. There's no degeneracies, but the density of states is exponentially small down to zero energy. And so it has something, a form of this type. Okay, so this result was in the appendix of this paper, actually. And we said, okay, this is not seen in any condensed matter system. So there's some pathological properties of this model. True enough. But at that time in 2001, I didn't know anything, neither did my collaborators, about black hole physics. If we had known, we would realize that, and this was something I pointed out a few years later, that these properties are exactly those that appear in Hawking's theory of black hole, quantum physics of black holes. So in particular, black holes have a ring down time or a damping time, which had actually been computed by Vishveshwara in Bangalore, which after Hawking had an expression for the temperature of black holes, you could then see was exactly this time, Planckian time, h bar over kT. And furthermore, if you took Hawking's result for a charged black hole, these are the so-called Reisner-Nordstrom black hole solutions, you find exactly the property that we found in the SYK model, which is that the entropy in the zero temperature limit is non-zero. Here, n is has gone to infinity. It's the number of degrees of freedom in a black hole, which is huge. But it seems to be that if for a charged black hole in the zero temperature limit, there is a non-zero entropy just given by the area of the horizon of the black hole, which is just related to its charge. Okay. And similar things also true for rotating black holes. This is something that Sandeep Trivedi has worked on in Bangalore, in Bombay, sorry. All right, so it turns out there's much more to this story than this. You can actually make a very precise mapping, which I'll just very briefly mention in the next slide. But what's happened since 2010 is now, I think string theorists have had a change of heart from the example of the SYK model. They realize that black hole entropy is not associated, zero temperature entropy is not associated with an exponentially large ground state degeneracy, as was the case in Pauling's ice model, and is also the case in various supersymmetric models of black holes. And there it's very clear it's an artifact of supersymmetry. But now there's finally an example of a physical system where you can get a finite entropy in the zero temperature limit, extensive entropy, and not have any ground state degeneracy, which seems rather fine-tuned. Okay, but so that's the qualitative connection. Now, thanks to the work of many people, including Kiteb and Maldacena, Stanford and Yang, there's a rather precise mapping. So I won't go into this, but you can start from Hawking's calculation of black hole entropy, which is sort of a semi-classical view of the quantum gravity path integral. But then for a charged black hole, you do a dimensional reduction, which is just a property of Einstein's equations, that when you go to the horizon of a charged black hole, the most important physics is just the S-wave component of the quantum fluctuations. The higher angular momentum fluctuations are higher energy. So effectively, the theory of gravity becomes two-dimensional, one space, which is the radial direction, and time. And that theory is now called Jakob-Teitelbaum gravity. So this was a reduction in principle Hawking could have done if he put his mind to it, I'm sure. But then from this 1 + 1 dimensional theory, you apply the principles of holography, which connects quantum gravity to entanglement on the surface. And it turns out that the theory you get on the surface, as pictorially illustrated here, has exactly the same low energy action. So you could start from Einstein's theory and get some low energy action here, or you could start from, this theory and get the same low energy action. And so that explains this connection here, and also has led finally to some new expressions for the density of states. This was Hawking's result, e to the area of the black hole. Then this cinch factor has come out from the SYK model. That describes the smooth function of the density of states here. And now this is beyond the SYK. We also know the prefactor and these strange powers through some very nice recent work of Luca Eliasiu, Murthy, and Joaquin Turiachi. All right, so that's it for black holes. So now let me get back to my home turf of the cuprates, and in particular, I'll try to discuss it in the general context of quantum phase transitions of metals. All right, so this is the famous phase diagram of the cuprate superconductors as a function of doping and temperature. And my focus here is on these metallic phases above the critical temperature. And there's, roughly speaking, 3 phases. Out here is an ordinary metal where you have a regular Fermi surface, as expected in a model of free electrons. And you have a rather mysterious pseudogap phase at low doping, which I won't say, I'll say a little bit about it, but it's clear it's not a regular metal, but it's got some rather bizarre Fermi surfaces and probably some kind of broken symmetry or more subtle topological order. And finally, in between is the strange metal. And the point of view I'll take for this talk is that these two phases, these two metallic phases here, the ordinary metal and the pseudogap, do not survive to 0 temperature, but they could in principle. So this we already know from, for the ordinary metal, we have the Kohn-Luttiger instability. Every metal ultimately is unstable to superconductivity. This one is more than most, but nevertheless, that doesn't mean we shouldn't think of an ordinary metal as a reasonable phase of matter, which could survive in principle to 0 temperature, apart from some weak corrections that we won't worry about to begin with. So the logic here will be, for various reasons I won't go into, that we should apply the same logic also to the pseudogap, that in principle, under just the right conditions, it could survive down to 0 temperature, but it doesn't really. But let's imagine it did. Let's imagine this phase and this phase both survived, and you somehow got rid of the superconductivity. Then there would be a quantum phase transition between 2 metals. And that's what I believe, propose, is the key to understanding the strange metal. Once you get up here at these high temperatures, the superconductivity is important, but for a moment, let's just not worry about it, and let's try to figure out how you go from these 2 states, and how do you get a strange metal in between. So that's the point of view, and this strange metal has some rather bizarre properties, like linear interresistivity, And the optical conductivity also has a 1 over omega tail, where, and these scattering rates. So this is the Drude formula, and if m star and tau are independent of omega, that's Drude physics, but they both have strong frequency and temperature dependencies. In particular, if you look at the tau of omega, it has exactly this Planckian form that I showed for the SYK model. So data like this were already appearing even in the early 90s, and was very much the motivation for studying this model. But then, we know now that the entropy doesn't vanish. It's not non-zero as temperature goes to zero. It vanishes. So this is good, but this is bad as far as the SYK model is concerned. Well, I'll return to that in a minute. But now the question is, can you understand these properties in terms of some kind of quantum phase transition between two metals? All right, so there's been a huge amount of work in studying such quantum phase transitions over the past 20 plus years. And in every model that you have looked at, you have two main ingredients. One is that you start out, let's say on this side, where you have this Fermi surface, and then you have a scalar field, phi. That's a key ingredient to the quantum phase transition. And invariably, this field is 0 on one side and non-zero on the other, as in the usual classical theory of phase transition. But now we also have to worry about the Fermi surface as a low energy excitations. And also this phi, it need not break any symmetry, as I'll discuss in a few minutes. So there's many different possibilities for phi. So one is that some Ising nematic transition that Steve Kivelson has worked a lot on, where you break some discrete symmetry of the crystal group, like rotation symmetry. And so phi is some order parameter measuring that broken symmetry. And the idea would be that near this critical point, you get some quantum critical fan, and strange metal behavior appears here. Or you could have magnetism, which would reconstruct the Fermi surface, in which case this would be, again, another order parameter. Or I think probably most relevant for the whole doped cuprates, in my opinion, there's actually no broken symmetry, but there's some kind of spin liquid physics present, that in addition to the mobile electrons that you see in the arcs, there's a background of resonating valence bond singlets. And these kind of transitions also are described by some scalar field phi, but now the scalar field phi is a Higgs field. It's a Higgs boson, not a regular boson. And so it carries, in addition, like the Higgs boson, it carries some gauge charges, which you may or may not have to worry about to fully understand the nature of the critical point. Anyway, so there's been a huge amount of work on such critical points and how you can have quantum phase transitions of metals at zero temperature, and certainly many claims that this is getting close to understanding the quantum critical fan. Okay, so let me now review some of that work and also some of the more recent ideas on how that work has to be improved to understand what's going on. So one model that's played a key role in moving this forward is not so much the SYK model, which was just a model of interacting fermions, but what now people call the Yukawa SYK model. And its motivation should be quite obvious. What we have to add to the SYK model is a boson, because that's what's needed for having a quantum phase transition in metals. So basically, you take this model, in this form studied by Ilya Estelitz and Jörg Schmalian. So you have fermions, and you have a boson, in this case just a bunch of oscillators, okay, for simplicity. And then you just couple them together in this Yukawa coupling. And now, unlike the SYK model, you make this coupling independent random numbers. Okay, so this has been studied just in the last few years, quite a lot. And the bottom line is it had essentially the same properties as the old SYK model now, It's got a zero temperature entropy, it's got Planckian dynamics, it's got all of those properties that I emphasized. And there's, as a function of the coupling, there is a whole extended region where you get this this SYK-like critical behavior. There's no phase transition here, but anyway, it's a zero-dimensional model, just like the original SYK model. This also has an instability to superconductivity, which is a good thing, but let's not worry about that for now. We want to understand what this phase is. So now this phase, of course, I can't jump and apply it to experiments. For one reason, the entropy is too large. It's got an extensive entropy as temperature goes to zero. I could apply it to black holes. It will give you all the same physics, but I'm not interested in black holes now. All right, so what do I have to do? So let's go back to now applying these methods to the problem of quantum criticality. So now let's be a little more realistic. So we have a Fermi surface, and then you have some scalar field, which we assume is given by some Landau-Ginzburg theory, and finally, I add the Yukawa coupling. All right, so one way you can formalize a lot of the earlier work and make it more systematic is you just give these things a fake flavor index, and then you solve this model. So this would be like solving the Yukawa SYK model with some additional spatial structure associated with the Fermi surface and the dispersion of these bosons. See, in the original model here, there was no Fermi surface and there was no dispersion. So you put those two back in and you work in 2 dimensions. And you solve the usual SYK-like equations, and you do find some version of these equations, as first shown by Patrick Lee, that you get some singular behavior of the fermion self-energy. So there's, in fact, no quasiparticles. They decay very rapidly, but the Fermi surface still survives. It's a sharp Fermi surface. It's sharp in momentum space, but it's very broad in energy space. And also, the famous Halpern-Lee-Reed theory also has the same properties with different exponents here. Okay, but now you ask, let's go back to this quantum critical region. Oops. Yeah, let's go back to the quantum critical fan and then ask, what does the resistance look like? All right, or the conductivity look like, because that is really the characteristic property of these metals, strange metals. So and there was a result in this paper by various people that there is a singular temperature dependence of resistivity and also a singular frequency dependence to the optical conductivity. But as you can see by the shading, now we know through the work of many people over the years that this is not correct. In fact, there's a version of Cohn's theorem that tells you that even though the system is not Galilean invariant, the low energy interactions are only very near the Fermi surface. And so if you're very near the Fermi surface, you cannot tell whether it's Galilean invariant or not. So you may as well assume it's Galilean invariant, and the result then is that the conductivity is in fact perfect. So this is the conclusion then for all of the 3 cases, that there is indeed at 0 temperature a very interesting non-Fermi liquid without quasiparticles. But is it a strange metal at finite temperature? The answer, no, actually, it's a perfect metal. You have perfect drag, if you wish, in this strongly coupled system, and it's not something that you can really use to explain any experiments of transport, anyway. All right, so that's where things were somewhere early in the pandemic. And we decided we have to really do a more serious theory of the effects of broken translational symmetry to understand what's going on. And this is where all the SYK technology came in very useful to us. How am I doing on time? Sorry. 5 minutes. 5 minutes? Okay. 10 minutes, perfect. Okay. So now I want to describe some work over the last few years with many brilliant collaborators. and this is still ongoing work. But I especially want to mention the role of Avishkar Patel, who's now a postdoc at Flatiron, who has taken made a huge effort to study a lot of this using quantum Monte Carlo, and that work has been really crucial in developing the understanding I want to present now. Okay, so let's go back to this theory of a quantum phase transition in a metal. We have a Fermi surface and a scalar field and a Yukawa coupling. And what I've just told you, this theory is inadequate because it has the constraints from translational symmetry are way too strong to understand the dramatic observations in the experiment. So we have to break translational symmetry. So how are we going to do that? Well, the usual way you break translational symmetry is by adding a random potential. So you take these fermions and you add a random potential, and if you just didn't have the scalar field, that leads to the well-known theory of weak localization, summarized, and then various Altshuler-Aronoff corrections, which were summarized in the famous review article of Lee and Ramakrishnan. And all of those effects are also present here, so maybe we have to worry about all of that. Yes, in principle you do, but it turns out there's a much stronger effect. That's far more important to worry about to get the right physics. And that effect is sometimes called Harris disorder. So one way to get Harris disorder is to imagine that your Yukawa coupling G has some spatial variation. And as this has spatial variation, it creates an inhomogeneity in the position of the quantum critical point. So if you look at this quantum critical point here, there, so one region of the sample, this critical point is somewhere here, somewhere else it's over there, because this critical point is determined by the value of G. Now, usually you put the critical variation in the mass, but for technical reasons, I'm not doing that, but you can put it there if you want. It gives you essentially the same results. Okay. All right, so let's put in, to begin with, some variation in the position of the critical point in the coupling G, spatial variation. And let's solve this theory. So now we have a tool for solving such theories, which is you give everything a flavor index and you take the large N limit and you get some self-consistent equations, which turned out to be just the right set of equations to understand black holes. So let's apply this here. Of course, here we're in a little bit more of a dangerous situation because you have spatial variations and the number of flavors is very small. But anyway, let's do it. Okay. So if you do that, in other words, you solve these equations self-consistently, you get, and this has got exactly what's observed, at least qualitatively. You get a linear anti-resistivity, which is determined by the spatial random coupling, but the transport is insensitive to the spatial uniform coupling. You get a marginal Fermi liquid self-energy generically and a T log T specific heat, all of which have various observational support. Okay. So here's some actual data where we completely solve these equations. So this comes from solving all of these equations numerically. So, this is as a function of some parameter, which is the mass term of this boson. The superconductor we also obtained, but I won't discuss that. But you get two regions, Fermi liquid behavior and a strange metal behavior. If you look at the resistivity as a function of temperature, there's a linear behavior near the critical point and a Fermi liquid behavior on this side. And if you look at the optical conductivity, I showed you this data of the real and the magnitude and the phase of the conductivity for different temperatures. And we get qualitatively very similar behavior from the solution of these equations. Then you can also look at the scattering rate as a function of frequency plotted here for different temperatures. And then if you rescale it with temperature, you get perfect, very nice collapse. And that's roughly what happens in the solution to our equations too. Anyway, so that's looking very promising, shall we say, certainly enough to get us excited. that this rather simple treatment of disorder, provided you include this Harris disorder, gives you, at zeroth order, essentially all the physics you need to understand the celebrated features of this strange metal. Another thing you find, which has also got us, encouraged us, I remember for the clean system, I talked about 3 different cases, whether you broke a discrete symmetry, whether you broke a continuous symmetry, or whether you had a gauge field, a Higgs boson or not a Higgs boson. They're all quite different in their properties. Here it turns out they're all the same. They give you essentially the same behavior. So disorder has this good effect of making everything look similar, which is also very encouraging because this, although if you look at the details of the phase diagrams of the pnictides or various organic materials or even twisted bilayer graphene and cuprates, they look very different. But if you look at the strange metal, it seems to be the same all across different families of compounds. And that's exactly what comes out from this Yukawa, 2-dimensional Yukawa SYK model. Anyway, however, that's not the whole story. So actually, let me jump ahead a bit. So here's the actual data for the strange metal, say in LSCO, shown as a function of hole doping and temperature. The red region is where you have the strange metal behavior. So what I've been describing so far is this what's called the quantum critical fan, this higher temperature region, let's say above 150 Kelvin, this goes up quite a bit higher, where you get linear intrusivity. And our claim is that in this region, you could take this model of quantum phase transition in metals with Harris disorder and treat it by SYK-inspired methods and really qualitatively get the right physics. And we're hoping eventually quantitatively. But if you look more carefully, and this is again true in many compounds, at lower temperatures, where you apply a magnetic field to get rid of the superconductivity, that's the white line, you have this, what's called the famous foot. This is the foot, where the strange metals really exist over a wide region. It's, of course, if you plot the resistivity from this high temperature region to this low temperature region, you don't see anything changing. The slope seems about the same, and that's something we don't understand at all. But when you look at low temperatures, there's definitely this foot. So somehow this SYK behavior has to break down, at least because it doesn't give you the foot at all. If you just solve these equations here, you don't get the foot. You get the fan, but not the foot. All right. So what's going on? So this is more very recent work. So what we looked at numerically, Avishkar looked at numerically, was the structure of the boson eigenstates. So you do a certain approximate treatment of the interactions, but you treat the disorder exactly numerically. So now no averaging or anything. And you look at the structure of the boson eigenstates. And if you're here at higher energy, this is the localization length of the boson. Sorry, I have erased the axis. This is the localization length of the boson in a 100 by 100 sample, and this is log of the energy of the boson. And if you look at higher energies, then this is what the eigenstates look like. They're really very extended, it's kind of random. And this is where we think that you could just treat this in mean field theory and understand what's going on. I'm sorry, SYK-like theories, and that's where you get the fan behavior. But if you look at the eigenstates at lower energy, at point C and point D, C, they're actually strongly localized, and then the localization length goes back up again. And we think we understand all of this, at least in the context of this model. And this very slow logarithmic increase is in fact connected to work by Daniel Fisher and others on the random transverse field Ising model, where these localized bosonic excitations, you can call them overdamped two-level systems, start to interact with each other, leading to a slow increase in the localization length. Anyway, so there are computations, which I guess I'm running out of time, of the resistivity and so on in such models numerically. And let me just summarize that they do, in fact, give the foot. So the bottom line is that if you take a theory of two-dimensional metals with Harris disorder, spatial variation in the position of some quantum critical point, there's a regime at higher temperatures where the bosons and fermions are all extended. And as long as they're extended, you can treat the disorder in an average manner and solve the SYK type equations, and you get pretty much what's observed. But when you go to very low temperatures, then what happens, and this is the most important point, is that the bosons localize, not the fermions. So the whole Altshuler, Aronoff, Lee, Ramakrishnan theory is about localization of fermions. That, yes, I think that may eventually happen, but it happens in a much longer length scale for these samples to be relevant. What happens much before the fermions localize is that the bosons localize, and that's what you have to account for in this theory of coupled localized bosons, which are damped by the extended fermions. And I believe that's the ultimate explanation of this foot-like behavior. And there's a lot of numerical evidence in some recent work with Avishkar, and also a quantum Monte Carlo work with Avishkar and Peter Luntz, which supports this interpretation. All right, so I'm done. So to recap, so the SYK model, what it has taught us is given us a solvable model of quantum entanglement in a model with no spatial structure, but you have a phase of entangled electrons which has no particles. There's no bosons, fermions, or anything. It's just these very complicated, complex many-body states which change completely when you go from one energy level to the next. And if you extend this model to 2 dimensions in what we're now calling the 2D YSYK theory and analyze it in different methods, we think it has a way of explaining much of the rich phenomenology of these metallic phases. And a bonus, from my point of view, is that amazingly the original SYK model has a dual description, which turns out to be exactly that needed to understand the low energy states of charged and actually also rotating black holes. So thank you.
Thanks, Subir, for finishing in time. So are there any questions? I'm sure there are.
So I was wondering for the Yukawa SYK T equals 0 entropy, what does that physically mean for the cuprates? I mean, what is that?
Oh, sorry, I lost mine. So first of all, there's many different models. If you take zero-dimensional Yukawa SYK model, if you take the zero-dimensional Yukawa SYK model, that does have an extensive zero temperature entropy. However, the model, I don't think that's present in the cuprates. Let me make that clear. It is present in charged black holes. It is physically there, and we understand why now. But it's not present in the cuprates. Then we solved not the zero-dimensional model, but the 2-dimensional Yukawa SYK model. That's the model we're solving. So that's a model. We're just calling it 2D YSYK. Well, that's what people are calling it. But now to that model, if you solve, what we believe happens, what happens if you just solve it in the SYK approximation, is you get a T log T entropy, which is exactly what's observed. So you don't get, the 2-dimensionality gets rid of the unwanted extensive entropy.
I see. So it's a related, connected question. So now if you take this in any dimension, Yukawa SYK, and then now...
No, you have to take it in 2 dimensions.
In 2D, okay.
Yes.
So then, but my question is that now if you want to project it into black hole physics, is there...
I will not project into black hole physics. So there's a separate question. What is the holographic dual of the 2-dimensional Yukawa SYK model?
Exactly.
I think that's an open question. I don't know if there is a good holographic dual. People are working on that question. But the natural black holes out there, if they're charged or rotating, they have nothing to do with the 2-dimensional YSYK model. They may be a holographic dual, but that's an open question.
Thank you.
Okay, there's another question from there.
Hi, Subir. Nice talk. I think I learned something. Yeah. So I'm curious though, with the application of the two-dimensional Yukawa SYK model to explain strange metal behavior, and
Yes.
as you said, it explains things in a variety of quantum materials. But which experimental observations does it explain, and which are still question marks? Or, so in other words,
Yeah.
what
Well,
do we
okay.
as experimentalists need to do?
Great question. So, we are obviously working very hard on that. So, the things I showed you were the resistivity as a function of temperature, and the optical conductivity as a function of frequency and temperature. And so we get linear T resistivity, which is quite ubiquitous, and people have different interpretations of optical conductivity, but I think the interpretation of Michon et al. For the cuprates, which only is relatively recent, I think is the correct one on how you should plot the data and do the scaling. And it gives you exactly the scaling that they proposed. Okay, so what in the cuprates, what are the things that you could try to, so the most famously, there's another property of the strange metal, which is the Hall angle, which has a rather bizarre temperature dependence. So we're working hard on that. Let's just say so with Georg Schmalien and Davide Valentinis and Avishkar, that's an ongoing project. I think we might be able to explain it, but yeah, I don't know yet. Let me not promise something we haven't quite achieved. So I think the Hall angle is a very important thing that we want to understand. We've also wrote papers on cyclotron resonance, and that's roughly consistent with Peter Armitage's experiments. We are also writing a paper right now on the thermoelectric effect, and I think that also seems to work. We have made some predictions for short noise. There are no measurements of short noise yet. There is Doug Neitelson experiment in a heavy fermion compound. So I think both the theory and experiment have some scope to do there. Let's see, I'm forgetting something else, but of course, we are also now trying to understand the onset of superconductivity, and there are some features of the superconductivity. For example, the slope of the resistivity has some correlations with TC. That seems to roughly emerge, but we haven't fully solved the equation to confidently claim that. There's something called Ohm's law that we also get discussed in our paper. I don't know. So in this field, I think it's hard to make a prediction because anything you could imagine has been measured by experimentalists. So we're trying to just catch up at this point. Yeah, we'd love to make new predictions, but yeah, maybe in the thermal power, there may be some things we can say.
Okay.
Yeah.
There's a question
Okay.
here, Janendra.
So along the same line, Subir,
Yeah.
here.
Yeah, there you are.
Yeah.
Okay, hi, Janendra.
So, I mean, it's very impressive that you can explain so many of these properties of the normal state, but does it give any insight into the origin of superconductivity and why the critical temperature is so large? I mean, something new about that.
Short answer is no. I mean, that's the disadvantage of having a universal theory. It works. It doesn't matter what this boson phi is. As long as the boson phi has some spatial disorder in acting on it, you get this universal strange metal behavior. So now we also believe that this boson phi somehow is very much connected to the onset of superconductivity. Now, if you will ask me my personal opinion, this is a question very much in my mind, of course. It's not so much the strange metal that's different about the cuprates, it's the pseudogap. The pseudogap, this well-formed pseudogap, let's say about 200 Kelvin to 400 Kelvin, with no broken symmetry and with no large Fermi surface, is very unique to the whole dope cuprates. No other compounds has this kind of pseudogap phase. And so it seems very natural to somehow conclude, and this is not so far from Phil Anderson and Bhaskaran's original picture, that's what's special about the cuprates and high TC. And what leads to high TC is some kind of spin liquid physics. Now, how to make that work and make it quantitative? Yeah, well, that's my next 5 years of effort, let's say.
Tanushree.
Yeah.
Hi, Subir.
Yeah.
Thanks again for a very nice talk. I was, maybe I missed it, so what's the origin for this disorder in G?
Okay, that's
how
a
do
great
I-
question. All right, so this is absolutely, I get this question all the time. So people say, I have a perfect crystal, it's a strange metal. Well, what? Okay, so the origin, I don't think it's fully understood, but let me just mention one data point. So the best cuprate is yttrium-124, which has no, it's a stoichiometric compound, and in principle is perfect. It's a perfect crystal in principle, and experiments would claim it's perfect. And so that shouldn't show a strange metal. Okay, but it does. So then we would say, oh, well, okay, there's a problem. Well, anyway, so what Bernhard Keimer's group has recently been looking at is the onset of charge density wave order in yttrium-Y24. And he finds that it has very strong charge density wave order. But when you go to low temperature, the width of the charge density wave peak doesn't go beyond about 30 angstroms. So there's obviously some disorder. So now I think my view would be that there's some kind of striped charge order that's forming. Now, there's a proposal by York-Schmalian that even in a perfect crystal, that stripe order will form a glass, maybe. There's always some disorder, so my view would be that even there is, due to interaction, there's some kind of stripe physics, and that gets pinned by whatever impurities are there. It doesn't take very much. So there's some intrinsic disorder, and all of these materials are just essentially impossible to get rid of. Now, one place people have managed to get rid of disorder is in a low TC material, which is rhombohedral graphene. Rhombohedral graphene is perfect, and that has no strange metal. So, so the theory is falsifiable. You give me a perfect crystal, which has strange metal behavior, well, then our theory is wrong. But I don't believe there's any examples.
Okay, so there is last question here.
Thank you for nice talk. Is there any effect of dimensionality, particularly anisotropy? Because if you go from undoped to heavily doped,
Right.
it changes continuously.
Yeah, so dimensionality, you meaning 2 versus 3 dimensions?
Yes.
Absolutely, 2-dimensionality is really crucial to get the linearity resistivity in the 2-dimensional YSYK theory. If you're in 3 dimensions, the effects are quite a bit weaker. So the dimensionality is key, so these kind of drag effects that I talked about are very strong in 2 dimensions. So when you go to 3 dimensions, then the usual perturbative treatment of Hertz-Millis type theory, I think is probably okay, but not in 2D. 2D, you have to treat disorder. There were many papers treating disorder in 2D, but they didn't really do it in the correct self-consistent way, where they've probably accounted for the disorder in the boson sector. Our papers were really the first to do that,
Okay. Okay, so the next speaker is Professor Avinash Mahajan from IIT Bombay, and he will be speaking on ruthenate, a zero-filled ruthenium-based Kitaev's quantum spin liquid. Professor Mahajan.
Thank you. Firstly, I would like to thank Tanushree and other organizers for giving me an opportunity to speak here. And this is especially so with very formidable, strong nearest neighbors, the one before, one to come after lunch, and several other very eminent speakers here. What I'm going to talk about today is, again, the spin liquid variety. Going to talk about some recent work that we have in a ruthenium 3+, so J effective equal to half based candidate Kitaev spin liquid. I am at the Indian Institute of Technology in Bombay. So I'm sure there are many in the audience who have either benefited from an education at an IIT or have collaborators there or at least aware of it. So some might not know that we now have some 23 IITs within the country, and here we are at in Kolkata somewhere here, and I'm here at IIT Bombay on the western coast. There are of course several others in various states nowadays. So the overall format of the talk is about this new compound, which is a ruthenium 3+ based honeycomb system. And we are proposing that this is Kitaev spin liquid without the application of a field, in contrast with this alpha ruthenium chloride, which is actually an ordered material, and it requires some 8 Tesla field to suppress the Heisenberg interactions and apparently see spin liquid behavior. So I'm going to talk about polycrystalline samples, and with some general introduction and motivation. So there are several in the audience who are experts in these areas and probably don't need this trivial introduction. However, maybe there are some others who would benefit from such a thing. So I'll speak about our bulk measurements, so susceptibility and heat capacity, and also local probe measurements through 7-lithium and proton NMR, and also μSR measurements down to low temperatures. So what is this quantum spin liquid? So there have traditionally been 2 approaches that have been taken. One is that you look for geometrically frustrated systems where all the nearest neighbor interactions cannot be satisfied at the same time. So a triangular motif is a very standard starting point in this. And then there are varieties. Of course, this is originally proposed by Anderson, and somehow this is linked to possibility of high TC cuprates, spin liquid being somewhere at the center of all that also. Now, how do you experimentally look for such materials? What validates that you actually have a spin liquid? So this answer is not so simple. So one looks for systems which structurally have this kind of geometrical frustration, and then looks at some bulk properties. So just simple magnetic susceptibility as a function of temperature. One wants Curie-Weiss behavior at high temperature with a negative theta Curie-Weiss, so indicating dominant antiferro interactions, and no order down to the lowest temperature that you can measure, which allows for a large range between the theta CW and either an ordering or absence of ordering, a large range of temperatures where you can probe this kind of spin liquid behavior. So you don't have any broken symmetry, but there is some possibly topological order in this spin liquid ground state. So many materials have been examined. In the triangular variety, you also have corner shed triangles, the Kagome materials. You have corner shed triangles in 3D. You have pyrochlore. So different types of materials have been explored. I think some should probably go out of the list now. This Na4IR308 shows a glassy transition, is no more thought to be a spin liquid. There is another view that is taken more recently. And of course, this is the work of Kitaev, same as showed by Subir, same author as showed by Subir in his previous talk. So he proposed a model Hamiltonian in 2006, which is, from an experimentalist point of view, would seem very strange. You have a honeycomb lattice and J effective equal to half sitting at each of these vertices, and somehow they interact with their 3 neighbors in different ways. So Ising-like interaction, but the red one connecting only the Z component of the spin, and the blue one only the X, and the green one only the Y. So very strange, but he showed that the ground state for such a system is a spin liquid, and this is driven by bond anisotropy. So in a real system, how do you engineer such a thing? Of course, you need something with strong spin-orbit coupling so that you can have this kind of bond anisotropy, and then hope to see a spin liquid. Of course, there's work which says what happens when these, in this parameter space of Jx, Jy, Jz, if you have isotropic one, you get a gapless spin liquid, Kitaev spin liquid. On the other hand, you can get gapped regions if the ratios are in some different ranges. And the excitations are also exotic. You get localized Majorana and itinerant Majorana. In real systems, how do you look for this? Because you always have this problem of Heisenberg interaction being present. So again, very important paper by Yakeli Khaliulin, they showed that you need edge-shared octahedra. So you have magnetic ions at these sites. However, you do have ligands which actually enable this super exchange. And if you have, so usually you'll have something O6, so RuO6, IRO6 octahedra. And if you have H shared octahedra, perfect 90-degree bonds like this, and then there is a cancellation of the Heisenberg interaction. So you need to look for honeycomb materials with H shared octahedra, perfect hexagon, and so forth. And then there is a phase diagram depending on various strength of various interactions. You can get a spin liquid in some region of this space. And again, is there a real example? Well, this absence of evidence being evidence, so no, you don't see any sign of ordering transition, and you have all the characteristics of this either Kitaev or otherwise in a geometrical frustrated system in this kind of geometry, then you say it's a spin liquid. Of course, there has been effort in looking at, say, fractional thermal Hall to look for these fractionalized excitations. So anyhow, so far actually there are these couple of systems. One is you need to look for systems with strong spin orbit coupling, so 4D, 5D elements in this place. And so this ruthenium and iridium based systems have been looked at. This alpha ruthenium chloride actually orders in zero field. You need to apply a field of 8 Tesla to move it, suppress the ordering, and apparently get a Kitaev spin liquid, although there is still some debate about that. There is another honeycomb based on iridium, and this is also thought to be a Kitaev spin liquid. So we have been looking at various 4D and 5D based honeycomb systems. So essentially what you have these honeycomb layers, so you have these honeycomb layers, and then in between you have some other ions. And actually you can change a lot of things here. In the honeycomb layers, you can put either a 3D element, say manganese, 4D element ruthenium, 5D iridium. In between the planes, you can put hydrogen, copper 1+, non-magnetic, silver 1+, and you have a whole zoo of compounds. So these have been popular among battery researchers in battery materials because you can move in and out various elements, so lithium, sodium, silver, etc. So in this family, the various possibilities, we have been looking at various of these. So iridium-based silver lithium iridate, it turns out it's not a spin liquid, it orders magnetically, though perhaps one could debate some features of a Kitaev spin liquid exist. Then one can do a mixture of iridium, ruthenium. There's again some motivation for that. But again, this looks like it orders 20K. There's a ruthenium-based Ag3Li Ru2O6. This is ruthenium 4+, so it's supposed to be spin 1. So we have done some work on that. The manganese one, the 3D one, orders magnetically 50K, like a classical system. So in all these, the interlayer separation is somewhat large. If you now bring down the interlayer separation, so this H3Li IR206 was worked on by Takagi. And here, by knocking out whatever is in between the layers and putting instead hydrogen, so this turns out to be J effective equal to half honeycomb system with Kitaev spin liquid-like features, and a small interlayer separation. So with this sort of idea in mind, we have looked at now a ruthenium-based system. I'll just tell you very quickly, how do we get this funny stoichiometry. So without going into the details of the preparation, so this is just a summary of what is known about the alpha ruthenium chloride. So with a field, some 7-8 Tesla field is needed to suppress the Tn, and then this part where there is a half integer quantized plateau, or perhaps just morning Subir was saying that still remains questionable. So anyhow, so this is the only one which has been looked at in great detail. So we're looking for another ruthenium-based compound which might show spin liquid features. So in literature we found that, of course, hydrogen intercalation in Li2IRO3, it gives this Takagi compound, D5, spin half, and so forth. It turns out in literature again, so this is various references exist, where you can do a longer time intercalation and push in more hydrogen. So you can go from H3Li IR206 to H5Li IR206 with now iridium in D4. You can go from 4+ to 3+. So we wondered whether we could do something like this in the ruthenium system. So you can start with Li2RuO3. So you think of this as Li4RU2O6, and then knock out the, this will contain some lithium within the planes, a center of the honeycomb, and remaining between the planes. Can we knock out the lithium and just put hydrogen? And maybe here as well, to start with, you have ruthenium in 4+, which is D4, which is supposed to be non-magnetic, and then can you go to 3+, which would be defective spin half. So it turns out that one can intercalate hydrogen. You can knock out the lithium in some low temperature process, and then come up with hydrogen lithium ruthenium oxide. So there's this question of how much hydrogen is there, how much lithium did you knock out, what is the ruthenium oxidation state. So I don't give the details, full details at this point. I just show, for example, the XPS, lab-based XPS, where we see that the binding energy for the ruthenium that we get is very similar to that seen in alpha ruthenium chloride, and of course different from RuO2, which is containing ruthenium 4+. So the claim is that we have a full ruthenium 3+ based honeycomb system, and then one needs to figure out the hydrogen lithium content. So the lithium content we calibrate starting with the starting material, and from NMR spectral intensity of the lithium, we finally come up with the formula H 5.9 Li 0.1 Ru2O6. Okay, so I just say that from the oxidation state of ruthenium obtained here, one needs to have a H-Li combination to have 6, and then Ru2O6. So now this is divided how much H, how much Li. So starting material is Li2RuO3. We measure the lithium NMR spectrum, and from the full intensity comparison of that and our final compound, we figure out the lithium content and therefore infer the hydrogen content. So what we have finally is H 5.9 Li 0.1 Ru2O6. It contains Ru3+ honeycomb structure. So what are the various bulk properties that we measure, and what do they look like? So as I said, for looking for a spin liquid, one is looking at heat capacity, bulk susceptibility, and other properties to look for any signs of order, any signs of glassiness, and so forth. So bulk susceptibility looks like this. You see an increase with decreasing temperature. Just note this is a log scale. However, there is some kind of broad anomaly around 40K or so. So one normally looks at low field behavior. So in low field, one does a zero field cooled and field cooled susceptibility as a function of temperature. And usually in glassy spin glass or frozen systems with frozen moments, you see some bifurcation between the two. Here we see none, at least in these measurements down to 2K. The third thing is that, so the green color here, this is the same data as this magnetic susceptibility. So at low temperature, there is a power law variation of the susceptibility with an exponent of approximately 0.9. Okay. What I show below, it comes a little bit later, but if you now subtract from the bulk susceptibility, not a Curie-like, very close to Curie-like contribution, what remains is this blue curve. So it's as if the susceptibility increases and then saturates at low temperature without showing any sign of order. You see, by the way, antiferro theta, this was another check. Do we have a dominant antiferro interaction? So about 40K. Okay, and this broad maximum is also about 40K. So the outcome, the result, what it's telling us, there's of course no ordering down to 2K. There's no zero field cooled bifurcation down to low temperatures at 50 Oersted. And so we are not going to have any spin glass or any frozen magnetism here. And the crossover point looks like around 40K from here. Okay. The other measurement that we do is 7 lithium local probe NMR measurement. So lithium sits at the center of the honeycomb. Remember, we have also knocked out a lot of the lithium. So all the lithium from the center, from between the planes has been knocked out, and more also from the planes. And whatever remains at the center of the honeycomb, that's what we are probing. So there are two important measurements from the NMR. One is the measurement of the shift. In metals, it's called the night shift. So how much does the resonance shift with respect to a diamagnetic compound? How does that vary as a function of temperature? And the other is low energy excitations. How does the spin lattice relaxation rate vary as a function of temperature? So based on various spectra at various temperatures, we obtain that the shift, so at high temperature, we don't, I mean, the shift is small, we don't have sufficient sensitivity, but it's almost nothing. And again, below 40 K, one sees an increase and then leveling off. You know, this is very much like if you subtract out the T1 over T to the 0.9 term from the bulk susceptibility, then what you get is very similar to what the shift is measuring. Okay, so it appears that we have something where the susceptibility at low temperature looks like has two contributions, some power law part, and then there's part which is temperature independent, which is what is sensed in this NMR measurement. Okay. Again, as I said, one also measures the spin lattice relaxation rate. So we have measured on the lithium nucleus, which is sitting at the center of the honeycomb, but also for the proton, which is in between the layers, but also at the center of the honeycomb. In these cases, we find instead of a usual exponential variation of the recovery of the nuclear magnetization, we see a stretched exponential, which is indicative of some inhomogeneity. There is also, so this is the spin lattice relaxation rate with temperature on a log-log scale, so one sees a power law variation below about 40 K. And there is some dependence on field. However, one can plot this as a function of T by B, and we see a data collapse, so whether it's the proton NMR or lithium NMR, once you plot relaxation rate with T by B, one sees a data collapse. Okay, and such a thing has been seen in the Takagi H3Li IR206 compound, and so might have a similar explanation. It's associated with defect states which have some dependence on energy and field, and then one sees this scaling. So what's the thing we have learned from here? Firstly, in this low temperature part, of course, it's a power law behavior, so we have gapless excitations. And also there is a data collapse with T over B. We are suggesting this comes from some form of the density of states for the defects. Also, there's a stretching exponent beta. We don't see a perfect exponential recovery of the nuclear magnetization. And this is about 0.5, 0.6. Somehow in all the spin liquids that have been looked at in the past, one often sees such stretched exponential behavior with an exponent about 0.5, 0.6 or so. The next thing I want to quickly review before I show the MuSR data is how this MuSR experiment is done. So muons are produced in some reaction in this collision. They are produced 100% polarized. So they have a spin pointing opposite to their linear momentum direction. So these muons are incident on a sample. They implant inside the sample. And then they precess about the local fields, and they basically, the muons are 100% polarized. They'll depolarize due to dynamics of the electrons in your system. So this is an indirect way to probe local moment dynamics of your system. Okay. What do you see usually? Well, what you measure is, of course, the muon is also radioactive. It decays in 2.2 microseconds. Gives off a positron, which is what is detected by these various detectors, forward and backward. And what one typically plots is this something called the asymmetry. So you count how many positrons in the forward, how many in the backward, and just look at the asymmetry. So here the exponential decay of the radioactive decay of the muon, that is cancelled out because you're doing NB minus NF by NB plus NF. The alpha is just associated with the difference of the detectors here. It's some technical thing. So one plots the asymmetry of the muon polarization and sees that as a function of time. Okay. So this is what one typically observes when, for example, so what are the moments that are dynamic? So one is the nuclear moments, and then of course you have the electron moments. So one usually sees this well-known Kubo-Toyabe behavior. So it has some Gaussian initial part, and then this has a minimum here, and it plateaus to a 1/3 of the final value because roughly 1/3 of the moments are pointing in the field direction. On the other hand, once you have electron spins, there's a chain bin behavior. If you have ordered material, then one sees oscillation of the muon asymmetry. As in the case of static moments. So if one looking for dynamic moment, one checks whether we are seeing any oscillations or not. And other point is there is the effect of the applied field, longitudinal field, in decoupling the muons from the internal field. So if you have dynamic spins, it's not easy to decouple the muons from the internal dynamic field. So one does a zero field experiment, and also one does a longitudinal field experiment to probe muon dynamics in order to obtain the basically properties of the electron moments in the system. So we have done measurements down to 77 milli-K, and we see no sign of any oscillations. So this is to be revised to now 77 milli-K. Also, this 1/3 tail in the muon asymmetry, which is usually there in case of some static moment, that is also not seen. We see the muon asymmetry going to 0. And it does not follow, in this case, a straight exponential. Not a single exponential, it has a double exponential feature. This is not very surprising. In some other honeycomb systems that we have worked on, we found a double exponential behavior. It's basically associated with muons stopping at 2 possible sites, and so seeing the dynamics from 2 different vantage points. So we see a double exponential behavior. The ratio A1 to A2 does not change with temperature. And then we track what these lambdas do as a function of temperature, and eventually also field. So here, for example, are data for various temperatures. So later I also show a lower temperature, 77 milli-K, but from room temperature down to lowest temperature. And you see, as at high temperatures, one sees this kind of curve. So smaller lambda. And as you go down in temperature, one sees a faster muon depolarization. And so one extracts the lambdas out of it and plots. So one sees a lambda as a function of temperature behaving in this manner. So increasing and then slowing down of the spin dynamics, but then plateauing below about 40K. Again, same temperature that we saw in the susceptibility and NMR. Okay. This is very, very similar to the Takagi iridium compound, which is spin half, again, possible Kitaev spin liquid. The difference is that in their case, the plateau appears below about 1K. We already have the plateau appearing below about 40K. So this is quite interesting. So the summary is that we see a flattening or saturation of lambda, so slowing down of spin dynamics. However, no sign of any ordering, no sign of any glassy behavior. Very similar to that of the honeycomb iridate, spin half. However, the effect sets in almost at 40K compared to about 1K in the iridium system. And of course, we see 2 components to the relaxation and with equal relative weights. So our feeling is that this is associated with 2 stopping sites for the muon, and this similar thing has been seen by us in Ag3Li IR26, another honeycomb iridate. So in Takagi's compound, of course, there are 3 components, so possible 3 stopping sites. Also has been seen in Na2IRO3. So you extend the measurements down to low temperature. So there are 2 different facilities. So the earlier one was at the PSI facility. This is at the ICIS, where we have somehow access only to the, there are 2 lambda 1 and lambda 2. We have access to the slower component. There's an initial gap there. So one tracks that, and of course down to 77 milli-K, you just see the plateau without any onset of any oscillations. So no sign of any order. One can also do measurements in a longitudinal field to see how the muon decouples from the internal fields and goes along the applied field, the polarization. And one way to look at it is that how the lambda varies as a function of field. So one is basically probing the electron autocorrelation. So in usual cases where there's no, so in standard cases, one sees a behavior with x equal to 0, one just sees an exponential autocorrelation. That sort of fit does not work very well. What works is this, where you have a extended, there's autocorrelation which extends over some time, and one sees better fit to that compared to just an exponential autocorrelation. So there are these long time correlations, but no static order. So this again indicating the standard characteristics seen in various other spin liquids. The other measurement that I will show is that of the heat capacity. So of course, one measures the total heat capacity, and then taking a non-magnetic analog in the tin compound, one subtracts that and obtains the magnetic contribution to the heat capacity. And so what is shown on the right is this magnetic contribution, Cm by T, as a function of temperature. So various significant features here. So A, there is a dependence on the field. So in the zero field data, so that is hidden here in this black open squares, one sees a increase as temperatures decreased. And with field, one sees a suppression of the heat capacity. Okay? So this kind of thing has been modeled in the other iridate compound, and we find we can again explain this low temperature increase in zero field with the T to the minus eta behavior, with eta approximately 0.9, same power as in the bulk susceptibility for the low temperature increase. The other point is that you can again plot field B to the power eta, Cm by T versus T by B, and they all collapse onto the same curve. And the power law, so all they collapse into the same curve, and this gamma, the power, it's a power which I show next. So where is all this coming from? So there has been a paper where they have discussed vacancy-induced low-energy DOS in a Kitaev spin liquid. So you have a Kitaev spin liquid, you can have vacancies instead of the magnetic atom, you can have a non-magnetic atom sitting instead of the magnetic atom, or some other extrinsic defects, and they can give rise to defect states, and basically one can probe the effect of this magnetic field, etc., and variation with temperature of this defect states in a Kitaev spin liquid, and some predictions have been made here. So for example, finite density of random vacancies in a Kitaev model give rise to a striking pileup of low energy Majorana eigenmodes and reproduce apparent power law upturn in the specific heat. So we have this power law upturn in zero field, so it's consistent with such a suggestion. Also, as a function of field, so they propose a field-induced flux sector transition where the ground state becomes flux-free for larger fields. So in zero field, you have a bound flux, and with increasing field, you make it flux-free, and then that gives rise to a suppression of the heat capacity, and then you get this scaling, which is also predicted. So this is the magnetic contribution to the heat capacity by temperature for various kinds of defects that has been looked at in this paper. And you go from a bound flux to a flux-free region as a function of field. Okay? So our suggestion is that this is exactly what we are seeing. Data are consistent if you model the DOS, defect DOS, as some inverse of energy to the power eta, and the density of states with field also in a similar manner, e to the eta, and also some power of the field. So our data are consistent with the eta equal to 0.9 and gamma equal to 0.8. The relevant number in Takagi's paper is, I think, 0.5. It's been suggested by some authors that level of defects can change these exponents. So this is just a comparison to show the data in our compound, heat capacity by temperature versus temperature, and similar data in the case of Takagi, where also they see a data collapse for B to the power half C by T versus T by B. We have B to the power 0.9 C by T versus T by B, and a similar data collapse is seen. So the other point that you can infer from heat capacity measurements is from the C by T, Cm by T measurements is the entropy change. And so here we have plotted the entropy change as a function of temperature. So firstly, the total entropy change we see is very close to RLN2, so for J effective equal to half. The other conclusions here are, in the context of predictions for a Kitaev spin liquid, where a two-step entropy release is expected because you have these two kinds of excitations, free Majorana and fluxes. And so the upper one consists of transition to free Majorana, and here's the entropy release correspond to the fluxes. And what is predicted is it should be RLN2 as the total entropy change at half RLN2 for the first plateau. And the ratio of the temperatures is also supposed to be TL, so T low by T high to be 0.03. So in our case, the ratio of temperatures of the low and high is approximately 0.03. The ratios of the entropy change are of course not quite half RLN2, but much less. So one possibility is that because of the defects in the system, this entropy change is spread over a large temperature range. And so either vacancy-induced effects or additional interactions over and above the Kitaev could be responsible for this deviation. Incidentally, in alpha ruthenium chloride also, I mean, it's suggested that the entropy change is half, but it's not clear where the plateau is, and the TL by TH is surely not 0.03. So to summarize this part, we have measured bulk magnetic susceptibility, seems to show a 40K change from increase to almost a constant. There's no ordering down to low temperature, and then the low T Curie like more maybe about 0.9. The NMR shift also shows a plateau below about 40K. The NMR spin lattice relaxation rate decreases below 40K and shows a power law variation, so gapless excitations. The muon spin relaxation rate, lambda, shows a slowing down, but then plateau at low temperature. All these are characteristics of spin liquid, and we see in the heat capacity broad peak, then a power law variation, and also two-step entropy release. So to summarize, I just put up this slide, so I've just said what the various results are. So we are suggesting that vacancy-driven effects in the low energy excitation of KQSL may be a novel way to probe the pristine state. So also, I would like to, of course, thank collaborators. Sanjay Bachar is the PhD student who did all the work. He's now a postdoc at Duke University. Sumiran Pujari is a faculty colleague at IIT Bombay. Michelle Bennett's, we did some measurements out there. And of course, the mu-SR measurements were done at PSI with Hubertus Lutkens and John Wilkinson at ICES. And of course, we thank all the funding agencies for their support. And thank you for your attention.
So we have time for some quick questions. Bhaskaran here.
First is about this hydrogen, because it's known that hydrogen has large zero-point fluctuations. So it's likely to average out because in the original compound, local distortion will not allow the cancellation of Kaliulin and Jacqueline. So if there is large zero-point, so that's one way by which the Kitaev component can be reduced. In fact, I made some estimate after listening to your talk last week. It seems to be working. And the second thing is these two steps in this specifically, that's a key feature of Kitaev model. So that's also encouraging. So it's worth pursuing the role of hydrogen. Thank you.
Thank you. Anyone else? Quick questions? Tanushree?
I'm just curious, is there a specific reason of this mixing hydrogen with lithium and like 5.9 and 0.1?
Yeah, so for different times of intercalation, we can get different amounts of hydrogen inside. So this is with some.
Just not by design, it just so happened.
So this was with 96 hours. We have now samples with different hours, so which have different amounts of lithium. Yes.
I see.
And so I have a separate slide on that, so we can calibrate how much lithium by looking at the NMR spectral intensity of the lithium.
Okay. And does it influence really how much this percentage of hydrogen versus lithium?
Yeah, it does, of course. Yeah. So we are looking at other compounds right now. We have not done the full measurements yet.
Okay, there's a question back there. Could you just stand up so the speaker can see you?
Hello. Yeah. So hi sir, nice talk. So my first question is when you showed the parameters, so your C was quite low, so the interlayer distance.
So
in the compounds,
quite close, about 5 angstrom.
Yeah. Which was lesser than A and B. So did you consider that interlayer coupling? Because
I have no theory here.
Oh, okay. Okay. So like because the Kitaev should be in the 2D, so the interlayer coupling might deviate from the Kitaev spin liquid state.
So you see, in the other iridium compounds, you take Ag3 LiIR26. It has an interlayer coupling of some 6 angstrom. It doesn't show Kitaev behavior. It orders at some 7-8K. But you replace by hydrogen, H3LiIR26, you bring down the interlayer coupling, you bring down the interlayer distance, and it has Kita efficient, it doesn't order. So, you know, just having hydrogen there also plays a role. The decrease of the interlayer distance also plays some role.
Okay. And the second question was when you showed that entropy is not half, it was 1/300. So is there any significant, like you said that it might be due to the disorder. So is there the role of like that stoichiometric ratio? Is there a connection with that 1/300 factor instead of half?
That is one possibility, and in addition to the Kitaev terms, maybe the other terms in the Hamiltonian. I mean, this is all speculation. We don't know clearly.
Okay. Thank you.
So let's thank the speaker. And before you go, I have something to give you.